This video is about finding the electric potential due to a finite line of charge. For example, we have charge Q evenly distributed along the y-axis from negative A to positive A, and we want to calculate the electric potential at some point, any random point on the x-axis. This is a 5-step procedure. The first step is to divide the distribution up into pieces, dq, and then step 2 is to find the potential due to each piece, dq. Step 3 is to write dq in terms of the variable that changes from piece to piece. And step 4 is to add them all up by integrating. And step 5 is to check our answer. So let's go back up and start with step 1. We want to divide this up into pieces such that each piece, dq, is the same distance, r, away from our hypothetical point P here. Okay, and basically what we're going to do here is we're going to say that V is the integral of all of the little pieces of voltage here, dV, contributed by each little dq right here. And the voltage we're going to calculate now, the potential due to this piece, dV, is equal to K times that little dq over R. So the potential due to a point charge is kq over r. So we're going to treat this as an infinite number of little point charges lined up from negative A to positive A and add up the electric potential due to each little piece of charge, k dq over r. Okay, so our voltage is then the integral from negative A to positive A of k dq over r, where r is the distance from the dq to point P. Okay, now r changes as I move from slice to slice. A slice down here has a different radius than does, for example, this slice up here. There's a different r there. So r changes as I move from slice to slice, and so I need to write that in terms of the variable y, which changes from slice to slice. I'm going to call this distance here from the origin out to P x, and therefore r is actually the square root of y squared plus x squared, where y is the distance, is the position along the vertical axis of my slice dq, of every individual slice dq. But then, since y is changing as I move from slice to slice and x is not, I need to rewrite dq in terms of dy, and that is step 3. So the way that I do that is to do a ratio. The little piece of charge dq over the total charge q is the same ratio as the length of the small piece dq, which is we're going to call dy, over the total length, which is from A to negative A, so 2A. That means that dq is equal to q over 2A times dy. Q over 2A is the charge per length of this particular line of charge, and the variable we use in physics for charge per length is lambda. So Q over 2A is lambda for this particular short line of charge. It's the charge per length. So now we're going to substitute dq in to our integral, and we're going to substitute r into our integral, and we're going to add it up. So now we have v is the integral, the sum from the bottom piece to the top piece, negative A to A, of k, and I substitute in dq, which I solved for as q over 2a dy, divided by the square root of y squared plus x squared. And now what I'm going to do is I'm going to factor out everything that's a constant. K doesn't change from slice to slice. Q doesn't change from slice to slice. 2a doesn't change from slice to slice. So I can pull that out. K q over 2a times the integral from negative a to a of dy over square root of y squared plus x squared. So this is not a real easy integral. So if you're in your physics class, your math class, your calculus class, your calculus teacher would show you how to integrate this, probably by trig substitution. But here in physics, we look things up in a book. We look things up in a table of integration. So on page A18 in your textbook, you will find the following. It will say the integral of dx, the variable, over the square root of a squared, a constant, plus x squared, the variable, is equal to the natural log of x plus the square root of x squared plus a squared. Now, in our case, a is x, because x is our constant, and x is y, because y is our variable. So we're going to write this out. We're going to solve this by substituting it. This is now kq over 2a times the integral from negative a to a of, actually I want to do the integral, so let me erase that. Let's substitute the answer here. This would be times the natural log of y, which is our variable, plus the square root of y squared plus x squared, evaluated at negative a and a. So I'm going to plug those in now. kq over 2a times the log of, plug in a plus the square root of a squared plus x squared, minus the log of, now plug in negative a plus the square root of a squared plus x squared. And I can simplify this a little bit just to make it look nicer, but basically I'm done. kq over 2a times the natural log of the quantity. This is log of a minus log of b, which is log of a over b. So numerator is, I'm just going to switch these so it looks pretty, a squared plus x squared plus a divided by, now it's minus a, square root of a squared plus x squared minus a. And that is our answer. So I will highlight it. Highlight answer. Okay, so check units, check answer. Let's look at our units. K, Q over A, that is the same units as K, Q over R, which is voltage. And then log, this in here is distance, square root of distance squared plus distance, so that's distance plus distance over distance minus distance. So the argument of the log has no units, which it shouldn't, and the log has no units. So basically my answer has units of kq over r, which are the correct units of potential. So let's recap really quickly. Let's go back up to the top. Line of charge divided up into pieces dq. Then the voltage due to a single piece is dV, which is k dq over r. Add those up from negative a to a. Substitute in dq in terms of dy. Substitute in the radius here in terms of y. Integrate by looking it up in a book, or if you want to do the trig substitution from your calc class, feel free to practice. And check your answer. And in the next video, not in this one because I'm running out of time, we will do the ring of charge.